joined Roadblocks in 2015, and almost soon after training, I joined the data science practice. So I heard about this thing starting up in our career, where they were doing many, mostly at that time they were doing proof of concept work, and I got interested in that. And since then, for more than a year now, I've been working in the data science. So the topic of my presentation is automating deployment of R models in production environment, and I have divided the presentation into four things. Initially, I will give a very small and simple of a basic data science task, mainly for those who are completely new to the and then a particular project which I worked on, what were the business requirement and solution we proposed, and so it was done in R, and then I want to know how deploying the solution to production was done. And in the end, I looked at some other methods we considered during the process and why we did not use it. So, how many of you here have used R? Okay, and how many of you have done some data science work? So there are some who have not, who are new to it, right? Probably. So here I'll explain one simple data science task. This is a generalized version of one type of machine learning, which is called supervised learning. So I'll explain it using one problem of the sales process. So in supervised learning, what happens is to use supervised learning, you need to know first of all exactly what is the thing you want to predict. So in the case of sales forecast, you clear that what you want to predict is the sales for say the next day or maybe the next week or something like that. And also you need to know what things affect that sales or what things decide what the sales will be. So it might be things like what was the previous week's sale. To give you some idea about what the sales is going to be. That and whether there is a promotion running or not, things like that. You need to know that, and you need to have sufficient amount of data with sufficient amount of observation of these variables. You need to have a couple of years, or depending on your problem, of data of observations of what was the sales, and during that time, what was whether there was promo happening or not, what was the previous day's sales. If you all have all that, you can do the supervised learning. The data I just talked about is called the training data. And the value you want to predict is called the resulting variable, and the things you use to predict it is called the predictive variable. So that training data you use that to train the model, and what you get is the trained model. And now when you have the trained model, you can give it new values of the predictive variables and get a resultant output. So if I give it this the week which passed, right? The state of that and details about whether tomorrow there is demo going to happen or not, etc. I'll get what the model thinks is going to be the same. So that's one example of a simple data science task. And most of the examples I use in my presentation will be supervised learning models. So if you understand this, you'll understand that. And now a little bit about R, which is the language we use for the project I'm going to talk about. R is a language and environment for statistical computing and graphics. And it is right now one of the most popularly used languages for business projects. And some of the reasons why it is very popularly used is one is that the packages in R itself, right? It implements almost all of the statistical algorithms we have, and the quality of those is very good. And another reason is that it's not always that when you do a data science work, the result you want to you expect the model. It's not always that's not the case always. Sometimes what you want to do is you want to get some plots and graphs to communicate to the business about the workflow. So even in that case, R is one of the best solutions, best options you have to so R is a tool in which you can do the analysis and also show the results as graphs and plots. The quality of the graphs and plots you can create using R is very good. There are other options like BPJS and all in which you can create very good looking graphs. But in that case, you'll probably have to do the analysis in some other language, get the data in the particular format which BPJS requires, and then do it. So R is one option where you can do both. So that was what I explained earlier. Also, earlier in that diagram was one data science task. Right? So when I started working with the data science team, I was working as I told mostly on proof of concept. And what happens in a proof of concept kind of work is your main aim is to show some result in the short time frame you have. You don't look at things like how the model will scale or how good the code quality is or how you will make the result available continuously on a real-time basis. Things like that. So later when I worked on an end-to-end project, that's when I learned a lot of these things and the rest of this presentation is going to be a lot mostly about that, what I learned in that project. So here this diagram shows the structure of complete data science project. So the first step, like any other project, you look at talk to the business, understand the business requirement, and you also look at what data they have and what data they are ready to collect. So after that, after you get an understanding of both those things, you come up with a solution which you can do to solve that problem using the data you have. And you propose that to the business. If they are fine with it, you go ahead, you take the data and you clean the data, some data preparation task, and then you model the solution you want. And once you have the model, you check the accuracy of the model, you validate it. You also check with the business again that they are happy with it. After all that is done, after the model is completely ready, now you need to deploy it to make it. So in the deployment, two things happen, right? One is that all these steps you did here, they are usually done by a data scientist, and during that process, that data scientist does not necessarily work with the rest of the application developers or whoever is going to be the end consumer. So a lot of things come into play when you actually take it deployment. And once you have the model and give it to the client, right now the accuracy is still very good. But after a couple of years, uh, the accuracy might not be so good because it was trained using old data, right? So you want to train the model again. And many times the client doesn't even have data scientists on their team. This is why they came to us. Right? So you can't expect them to do the training again when after whatever time. So you have to automate that process. That is one of the steps which comes into play. And another thing is that once you've made the model, you probably also have some code which uses the model to do the prediction, right? You have to, when these first steps are done, that code is probably just sitting in some data scientist's laptop. You have to make that available at real time so that an API or an application which is going to use it can just send a request and get the prediction and show it in whatever user interface they are thinking of using. So that was about a general structure of a project, a data science project. Now I'll talk a little bit about the particular project I was talking about, right? The business use case and all, and how we did the deployment in that case. So the client I'm talking about was a non-profit that provides micro loans to underserved communities, like people who don't have access to the usual way of getting loans from banks. And so their business requirement was that at that point they were using something like a third party people to decide how much loan to give to each applicant. And they wanted to scale their operation, and for that they couldn't rely on third party people because it requires certain type of skill, right? It's not like they can just take any person and use them to decide how much to give to each applicant. So it was difficult to find such a person in each village. So they were thinking of using machine intelligence to do the same. So, and they already had something like a credit score in mind. You know, credit score, like banks give people credit score, basically tells them how good it is to give that person a loan, how much chance there is that that person becomes it. So they had something like that in mind. But when we looked at what data they have and they are ready to provide, mm, the data they had did not have anything like customer ID. So they had data only at loan level. The data they had looked something like information about the applicant and how much loan was given given to them by that third party person who was deciding how much to give. So it did not have anything like a customer ID, and even if a customer A, say, had taken some 5 loans in the past 3 years, you had data regarding all these 5 loans, but nothing to tell me that all these 5 were taken by this one person. So without data like that, credit score was not something feasible. So instead, we proposed a solution which was a classifier using logistic regression. What it does is it looks at it trains a model using all the past loan data, and the model you have, what it can do is it can just take all the information about the new applicant and tell you maximum amount of loan you can give. Basically, the same thing that the third party was doing. So if you remember the diagram I showed you initially, right, about the general data science class, you can relate this to that. This part here is the training data, and these three, the financial status, the purpose of the loan, and some other demographic information about the applicant, they are the predictor variables which we think will affect how much loan we should give. And they are basically the variables they were looking at initially to decide how much loan to give. And the output variable we know is the loan amount or the upper limit of the loan which can be given to that. All this data is used to train the model, and after training the model, the same variables, new values are given for every new applicant, and you get a loan class. Once you have the loan class, you basically compare that and the amount that was requested by the applicant. If that falls within the limit, you give the amount, otherwise, you. Yeah, so what we did was, what we had in place was logistic regression. Once you, it basically gives you probabilities, right? Probabilities for falling into each of these. And what we did is we summed it up. Like if the probability of being in say class, we have 5 classes. The topmost class 5 is the gives you the probability of being say 9,000 and above. So if the probability of being 9,000 and above is more than the probability of being the rest of it, then we say that that person be given more than 9,000. And if the next one, which we sum it up to say the next class which was 5,000, if it is more than that, only then we actually compare with the 9,000. So we actually start from bottom. Say the bottommost class is 3,000. We first check if that person can be 3,000 above or not. If no, we write them, classify them as 3,000 only. If it is so, then we check the 5,000 amount. Yeah. Yeah, we decided to separate. No, if you do this step by step, if you look at it as, one step, the bottommost step, whether we can get above that or not as one logistic regression classification, then you can do it, right? Yeah. So 2 and above is the other option in that now. Above 2 and below 2. Then the next step, only if he passes that 2 are the threshold, right? Only then you check the 5 above or below. The model, I'll get back to you on that. And so that was the model we had. And now to the deployment part. So the work, in the deployment part, as I explained earlier, there are 2 steps. One is to make that this cycle continuous, and another one to actually make the result available ready. So for the first one, we used Apache Airflow, and for the second part, what we did was we stored the model as a blob in database, and the code to actually use the model to do the prediction was also written in R, and it was running on R Apache server. And so now I'll describe a little bit about R Apache and Airflow, things we had used for deployment. Apache is a project supporting web application development using R and Apache. So, Apache is modular, right? It has one module to take care of different types of features. And in R Apache, we have a module called mod R, which embeds R interpreter on the server so that you can run R code on it. It also provides root support. Root is an R package which helps you create web applications using R. So in the Apache config file, you have this piece of code. So when a request comes, in the URL, if that classify on that part is there, Apache knows that our handler is what handles the request. And then it checks with each of its module to see who deals with our handler. And R Apache is the one which deals with our handler. So the next line, this R file eval line is actually evaluated by R Apache. And what RFRC does is, it looks at this line as actually two parts. This first part is passed through an R file, and the second part is an expression. So RFRC creates an R environment and runs each line of code in the R script. And after doing that, in the same environment, it evaluates the expression. The expression actually consists of a root application. It calls a root application. This classify alone is a root application which is defined in that R file. And inside the root application is the code to actually use the model to calculate the result and return. So this is the root application. It takes one argument, an environment, which includes the all the request parameters which came in with the request. Like it will include, in the case of the project I was mentioning, the all the information about the applicant, like their financial status and all, which is used to calculate the calculate the loan. So from the environment, all those parameters are taken out, used to calculate the loan amount, and the result is returned by creating a response object. All that is done using root package objects. This again shows the two parts in the deployment. This is the workflow pipeline we had. The steps we had in that is, one is to import new data. As when you want to do a training, you get the data again from the DB. Some data cleaning tasks are there as a step, and then the training of the model itself, and persisting the model into the database as a blob, as I mentioned. And the Apache server, every time it starts, it loads the data model from the database, and that happens only once. It's not like every time you send a request, it has to get from the DB. It happens only when the server is started, and this part is what I described earlier. A request comes, the root application calculates the prediction using the model and returns it. Now a little bit about Airflow. Airflow is a platform to schedule and monitor workflows. And in Airflow, each workflow can be looked upon as a direct acyclic graph. This shown here is an example of direct acyclic graph where each node is a task. And direct acyclic graph, you might be knowing, is basically it is directed, which means every link is directed in one direction, and it's acyclic, so it has no loops. And each task is the node we're talking about here. And in Airflow, the computation is done using Python. This is an example of creation of one direct acyclic graph of one workflow. So you basically create one tag object, and into that you can put any number of tasks. So each task is dealt with by an operator depending on the type of task. So if what you want to do is run a bash command, then you use a bash operator, and you give the bash command in this whatever bash command you want to run. If it's a Python operator which can be used to run a Python method, in that case the Python callable you give is basically the name of the Python method. Other than, and the last line of each task basically assigns the task to the DAG in the, of which it is a part. And other than this, it also has a task ID, a unique task ID. And this here is an R operator which we had created because we wanted to run R script. We could have done that using bash operator also, but we wanted to pass some R environment variables also to that. So that is why we created an R operator. And what we pass to it is the path to the asked which we want to run. And after defining all the tasks, you want to set the dependencies, right? Between the tasks, what happens first, what will happen later. For that, there are two methods: set downstream and set upstream. So here only set downstream is used, and T1 dot set downstream of T2 basically what it does is says that T2 is dependent on T1. It will happen only once T1 is completed. Okay, so that is the explanation of the project which I worked on. Some of the roadblocks which we had, one was the model size. So R, what it does is, in some of the model, it creates, it stores part of the training data also in the model, and that makes the model easy to store in database. How we solved that is simple. We looked at the model and saw that only some of the things were actually being used to do the prediction, and other than that, whatever was there, we manually did it. So that made it possible to fit that in the database. And another thing is that in this project and in many other projects, when the data science work happens, the data scientist does not have much of a contact with the rest of the people who are building the application is going to use this as an user. So that brings in some extra work which has to be done by whoever is going to deploy. To solve that, well, you can have the data scientists have more continuous communication with the rest of the team. And now I'll go on to some of the other methods which we considered while doing these two things, which was making the data modeling process continuous and making the model accessible. One is PMML. This actually I had not heard of why we were doing it. So I came across the data when I was searching for the presentation. PMML is predictive model markup language. What it basically does is it's a standardization sort of representing a model. If you have a model in R, you can convert that to PMML format, and then later from that PMML format, you can convert it into a Java model. So, but the constraints involved are that, of course, PMML should support both these languages, and also in PMML, you can't represent all the models. There is again a constraint on that. You have to see if PMML supports that particular model you're planning to do. And then there is R Shiny, which again is an application which helps you create web applications using R. And this third one is what we went for, storing the model as easy. And we can actually, the code written to use the model to compute the result, right? You can do that using some other language or using R. What we did was we had R script run. We wanted R script to run on the server, which is why we used R. And for the pipelining part, you might know there are many other tools like Uzi, but the reason I choose Airflow over Uzi is that in Uzi you write the syntax is using XML, right? And in Apache it's Python. So it gives a lot more flexibility to what and possibilities of what you can do in that than in Uzi. And another thing is the UI in Airflow, right? It already provides you with a UI using which you can trigger tasks and monitor the workflow. Usually you have an API using which you can create your own UI to see these things. But in Airflow it was already there. And that was also a requirement. That's why we chose that. And about the language itself, we saw a lot of things we had to do to make the model in R usable, right? So why did we choose R? There are a lot of other languages commonly used for data analytics. This survey gives show some of them. This is only one of the survey in which R is on the top. On the others also there are some differences, but R is consistently on the top. And there is one in which Excel was more popular than R, but Excel doesn't have all the most of the machine learning abilities. So, and one reason is that Python. One reason of popularity of R over say Python and all is that R is the language in which whenever a new say statistical algorithm etc. is invented, right? R is the language in which first gets a package gets created to do that. Python is catching up, but there are some things in R, like some very good models do time series analysis and all, which are not available in Python. And there's also, these are some of the factors you can use to compare these languages. There is also the thing about cost. So MATLAB and all, which are not free, might have a lot of libraries which you require, but then because it's paid, you can't use them. And another thing is the documentation. In R, if you look at the help file of any package, right, it's very much in detail and it's created by statisticians, so it's at a very scientific level. It's really easy to understand and it's really in detail. And as I talked about already, the graphics part is really good in R. And the speed was initially a problem. R uses RAM space to store the data while it's processing, which is kind of a problem if you don't have enough RAM. And but for the speed problem, now there are libraries in R which actually make it possible to run into things parallelly and increase the speed. Depends on the data you process, right? So depending on amount of data you have, you need that as well. The RAM is how much RAM? I think we had only 1 GB. Yeah. But if you're doing something like something at the level of how much data you use when you're doing a neural net or something, at that level it may not be. I haven't tried it. Otherwise, for most of the algorithms you usually use clustering the servers. Again, not something I've tried. Mm. So, continuously training process, do you mean to say that we can always add more data and get better results? So it depends on one thing how much data you have at hand. It's not always you have entire data, right? They might have started collecting the data at some point and you have a data. And also you will start to observe that after a point additional data is not interesting. So that you have to stop. Because the trade-off between getting more data to train it versus how much it's improving shows that it's not improving it much, then you use that model. Or it depends on the business requirement itself, how much accuracy they require. If it is some problem like some medical health related problem, I don't know, you probably go for more accuracy, spending more time, investing more time and money. But it's always a trade-off between. Yeah. Continuously. So continuously including data part, that how I understand is that is more, there is a threshold below that if you don't have at least that much data there will be a overfitting problem. But after a point it's more about having latest data, especially if you're doing something like in most cases you need latest data. It's more about having the latest data than the amount. Yeah. The amount of data matters to a certain extent, but why you need to do that training thing continuously, another reason is because you need the new. So in our project, the data was we did it manually only. I think you require tools depending on how noisy the data is. We got the data in Excel. Yeah. Yeah.
So that you have to do manually, but you can get it in any other forms. So the manual work is quite laborious, right, for data preparation to make sure the data is correct. Yeah, it is. But part and parcel. The most time consuming but the most boring part. Yeah. Yeah. We could solve it using a rule based. I think it is that. So in that case, what you'll possibly do is you'll have to what you'll basically do is you'll look at even rule based, right? Create those rules. What you'll be doing, you'll be looking at past data. See that a person has more than 1,000 rupees income. He defaults in 5 out of 10 cases, something like that, right? So here in this case also, when you're finding out what those thresholds are, they're kind of doing the same thing. So I understand. No, the question he is asking, just a background, I've done this credit scoring stuff manually. Okay. Both of the banks with just a paper and pen for a few years, and then with the Excel sheet for a few years. Set up the credit bureaus for I've never used any machine learning tools for everything was manual. Question he is asking is, what does that machine learning makes it so different? Because the four parameters that you said, and the statistical prediction, correlate with the research, and reduce it, and see that this is a model. That comes with some extra side and get to the company, it passes, then you say. So what is so done in the machine learning thing that is not able to do it in Excel sheet or do it? What is that specific thing that a machine learning can do? Simply the problem is if I understood correctly, you have a formula for simple interest. That is something the bank has decided. Right? So, so So one thing I can think of which is kind of quite different is what I explained you was supervised, right? So you can use not a supervised algorithm to figure out new things which might happen. So in this case you have to have some idea. If you're doing a rule based thing, whoever the person is, the experienced person, has an idea about what are things lead to a person not repaying a loan, things like that. Right? So if you there are machine learning algorithms which you can use to just give it the data and it will figure out that these are the things that yeah. So that is one new level of thing.
whatever that term or whatever you get, that plot, it's not always able to have a fixed empirical function. It might be a one-sided function, a complicated, a complex function, a compound mixture of a lot of functions. It will be like some whatever a linear combination of functions. That's how this all these linear models are people with the logistic and works on trying to guess what the function may be and then fine tune it. So that fine tuning is basically the so whatever the model she talks about is the final guess of that process of how the actual the underlying function is. So that is what machine learning is. If we have an intelligent model, we don't have to get machine learning. But if we can't guess what the function is, then we have to get machine learning. In real world applications, most of them it's not possible to guess the exact term. That is why machine learning is very sufficient.
Again, like rule-based system that we just said, like what we just described as a rule-based system is like an algorithm, right? If you use machine learning, maybe it can find a way that's more efficient than like guessing that if a person has more than how many keys, and guessing how many keys will be forward. So essentially, what they do manually, the computer will do. A computer will use past data to find a better way to get it.
More or less, rule-based system, you have to set all the rules. Machine learning, you let the computer do the work, give it some base rules, let it do the work,
You
and
can
then it becomes right or not. So you get results from it. More or less.
A quick time check. Thank you, Sophia. So let's have a short break before the next stop. The cafeteria is over there. The washrooms are